Philippe Archambault nous a parlé de biodiversité marine. Dominique Berthaud vous parlera de biodiversité plutôt terrestre demain. Donc pour notre prochaine conférencière, donc on a beaucoup parlé de changement climatique jusqu'à maintenant. On va passer un peu plus à l'anthropisation et donc pour parler plus précisément de pollution. Donc cette conférence nous sera donnée par Cathy Lowe, qui est une météorologue de formation, spécialiste de la chimie de l'atmosphère, qui a obtenu un doctorat à l'université de Cambridge en 1991, qui est maintenant directrice de recherche au laboratoire Atmosphère, Milieu, Observation Spatiale, plus connu sous le nom de LATMOS à Paris. Elle s'intéresse au transport atmosphérique de la pollution sur de grandes distances, ainsi qu'aux processus qui affectent l'ozone troposphérique. Elle combine modèles mathématiques et observations, en particulier les observations obtenues à partir de campagnes aéroportées. Parmi ses nombreuses activités, elle fut notamment coordinatrice du programme d'année polaire internationale Polar 4. C'est à cette époque qu'elle a commencé à s'investir fortement en Arctique. Elle nous présente aujourd'hui une revue des enjeux scientifiques en Arctique liés à la pollution et elle nous parlera plus particulièrement des sources, du transport et des impacts. Merci.
Voilà. Merci Marcel. Pour être plus clair, je suis désolée, mais je vais parler en anglais. Donc j'espère que vous avez vos casques. Okay, so I'm going to talk about Arctic pollution, and in particular the sources of Arctic pollution, the transport of pollution into the Arctic, and the potential impacts or the impacts of Arctic pollution. So this is an outline of my presentation. First, I'm going to begin with some motivation about why are we interested in looking at Arctic pollution at all. And then I'm going to divide the rest of my talk into kind of two parts. First, looking at long-range transport of pollution to the Arctic from mid-latitudes, because this is the main source. Up to now, this has been the main source of pollution in the Arctic. And then I want to say something about local sources of Arctic pollution, which perhaps are already important and which may become important in the future. And then I'll finish with some conclusions and perspectives. But first of all, what is Arctic pollution? Well, there are various different sources of pollution. So I'm going to talk mainly about ozone and also about aerosols, which are formed from anthropogenic emissions, from natural emissions, which are emitted primarily in mid-latitudes and then transported in the atmosphere to the Arctic. But then there are other sorts of pollution, particularly which we can kind of group together into toxic substances. So these are these persistent organic pollutants, these polycyclic aromatic hydrocarbons, such as anthracene, these PAHs, and also heavy metals, such as mercury. And these can be transported in the atmosphere, but also in the oceans, in the river systems, and also they can be stored in sediments. And there's a lot of recycling between these different compartments. But in this presentation, I'm going to focus mainly on air pollution, so on aerosols, so particles in the atmosphere, and on ozone, which is a pollutant and a greenhouse gas. And then if you're staying for the rest of the conference, there's a talk tomorrow focusing much more on toxic substances. Plus there'll be other presentations and posters during the conference. So why are we interested in air pollution? Well, we've seen some figures similar to this already today, showing the sea ice decline, and in particular the fact that the observations show much faster disappearance of the summertime sea ice in the Arctic compared to current climate models. And that's shown in this bottom figure here. You can see different results from the models that have been run for the current IPCC exercise compared with the observations. And there's a lot of possible reasons why this might be the case, but it's certainly related to how the models are treating atmosphere, ice, and ocean feedbacks. And one possible issue for the model is how they're treating Arctic clouds and how they're treating interactions between aerosols and cloud properties. And of course, this disappearance of the sea ice has big implications for Arctic shipping, the opening up of the sea routes in the Arctic, and also the exploitation of resources as the sea ice disappears, but also as the Arctic warms up. And these are also sources of local pollution. Related to this, we've already heard about this today, is this Arctic amplification. The fact that the Arctic is warming faster than other regions of the Earth. Of course, this is mainly due to rises in CO2, but pollutants such as ozone and black carbon, they also warm the atmosphere. And there are studies showing that they might be having quite a significant impact in the Arctic as well, on global warming and then on warming in the Arctic. And then methane is also an important greenhouse gas, which produces warming. So in this respect, we can pose some motivating questions for why we want to look at Arctic pollution. So first of all, what is the contribution of pollutants, so ozone and aerosols, and methane, to Arctic climate change? And in fact, there's a lot of interest in this topic, particularly at government level. Governments are interested in looking at mitigating these so-called short-lived pollutants. There's a new initiative, the Climate and Clean Air Coalition, organised by UNEP, where they're looking at mitigating the gases which produce ozone and also black carbon aerosols as a way of limiting global warming, but also warming specifically in the Arctic. And then the second question of interest is, to what extent will Arctic warming lead to new local sources of Arctic pollution? So shipping, oil and gas extraction, and what is their impact, possible impact on climate, regional air quality, and ecosystems through deposition of pollutants to the land and to the ocean. So now I want to just give a bit of background more about ozone and then aerosols. So ozone, it's what we call a secondary pollutant. It's produced from precursor gases such as nitrogen oxides, carbon monoxide, hydrocarbons, and methane. And it's produced largely over source regions in the mid-latitudes. And then because of its lifetime in the atmosphere, it can be transported long distances, including to the Arctic. It can also be produced during transport. So it's produced from anthropogenic emissions, such as power generation, vehicles, also from shipping emissions, agricultural fires. It can also be produced from natural emissions, so from forest fires and lightning, for example. And in terms of impacts, ozone, even at rather low concentrations, can have an impact on human health and also on vegetation through deposition of ozone to vegetation and crops. It can have an impact on the growth of these crops, of different crops. And then it also has an impact on climate through its role as a greenhouse gas. And there's been a study showing that possibly that 25% of the change in the surface temperature in the Arctic over the last 100 years or so has been due to changes in tropospheric ozone. Now, aerosols are somewhat more complex. There's many different types of aerosol, and they're often mixed together. They don't exist singular by themselves. So there are sulfate aerosols, for example, nitrate, black carbon, organics. And they have different types of emission. They have anthropogenic emissions, so again from combustion, from industrial processes, from agricultural fires. And then there are also important natural emissions, for example, coming from the oceans. There's production of sulfate from DMS emissions from the ocean, sea salt, and also boreal forest fires and dust as well is an important source. Now, aerosols have many different impacts. They can impact regional air quality through health impacts, even at very low concentrations. They affect the visibility in the air, so this is often seen as a phenomenon called Arctic haze at high latitudes. And then they can impact the climate in different ways. So certain aerosols, such as I've mentioned already, such as black carbon, can warm the atmosphere, whereas other aerosols like sulfate actually cool the atmosphere. You can also have deposition of aerosols such as soot or dust on snow and ice, and this can change the surface albedo, and perhaps it contributed to the sea ice melting somewhat, but perhaps another effect is also to affect snowmelt over the land and lead to earlier snowmelt over the land surfaces. I already mentioned that there are important and very uncertain interactions between aerosols and cloud properties. And there's been one study which is, well, a very large review, in fact, of more than 100 pages, which has shown that black carbon, in fact, may be the second most important warming agent after CO2. And this was including direct and indirect effects. And then aerosols are also important because they can be deposited to ecosystems. So you can have acid deposition of nitrate and sulfate to ecosystems. So now I'm going to consider long-range transport, which, as I said, has been up to now the major source of pollution to the Arctic. So I'll show some observations and also talk about the transport pathways for aerosols and their origins, and a bit about pollution processing during the transport. So in fact, this is not a new issue. This shows a quote from Norwegian explorers back in the 1880s, published in Science, and they reported kind of fine grey dust existing on the snow surface. But I guess at that time they didn't have that much idea of where this came from. But it is what they were probably seeing the result of was Arctic haze. And this shows an example of a kind of haze event. This is Ny-Ålesund in the north of Norway. And this is, in fact, an agricultural fire which was transported from Eastern Europe towards Svalbard during the springtime. And I'll come back to this event. So in fact, this Arctic haze is also not a really new phenomenon. It's something that was first observed by pilots in the 1950s. And then, since then, people have realized that, of course, as I've said, there are a few pollution sources within the Arctic itself. The Arctic is rather remote from major pollution sources, and so the pollution is arriving by this long-range transport. And another factor that's important is that the removal processes in the Arctic are rather slow. So, in fact, you can have a build-up of pollution during the winter months. And this is also helped by the transport patterns. So, in fact, in the winter months, which is kind of indicated by this blue line here, the Arctic front is much more extended. So this is the kind of barrier between the polar air masses and the mid-latitude weather systems. So, in fact, this facilitates the transport of pollution, particularly from Europe at low level and Asia and North America at higher levels into the Arctic. Whereas in the summer, this Arctic front covers a much smaller region. But in this case, higher latitude sources become more important, such as fires in Siberia and Alaska and Canada. So then if we look at surface observations, what we see is a clear winter maximum in pollution, in this case of aerosol, in the winter. So this is data from Barrow in Alaska. This shows the seasonal cycle of sulfate and nitrate aerosols with this clear winter maximum each year. And this, as I've said, is coming mainly from transport of pollution from Europe, but also from Asia more recently, and also from North America. And another important source is emissions from fires, so from agricultural burning. In fact, this became apparent during the International Polar Year, that agricultural burning in the spring and the autumn is also an important source of pollution reaching the Arctic. And this tends to take place during the spring and the autumn each year. And then you have also wild boreal forest fires taking place in the spring and the summer. But these fire emissions, they have large year-to-year variations. Now this shows, I'm going back to this photo that I showed you a bit earlier, this event that reached Ny-Ålesund here. And this, as I said, it was from agricultural fire emissions in Eastern Europe and Russia, which led to the transport of a huge pollution plume to the north into the Arctic. And in fact, the surface measurements showed new record measurements for practically all observed compounds, so carbon monoxide, black carbon, etc. So this was a kind of, perhaps a rather extreme event, but it was a very interesting event to study. But the data I've shown you so far has been at the surface, but what's happening aloft? Is it the same story? Well, this is also some data collected during the IPY in spring 2008. So it shows vertical profiles of aerosol between the ground and 6 kilometers. And what you can see are enhanced layers of aerosol. And in fact, these layers contained a lot of organic compounds, and in fact, they came from fires in Siberia. So there was a suggestion of having higher concentrations aloft compared to the surface. And in fact, we now have kind of new information from satellite data. This is an analysis using the Calypso satellite. So this is showing aerosol distributions at the ground between 0 and 2 kilometers compared to aerosol at between 5 and 7 kilometers. So close to the ground, you can clearly see aerosol enhancements here north of Europe, but then the central Arctic is relatively clean. Whereas if you look higher up in the atmosphere, you see that there, in general, is higher concentrations of aerosol. So perhaps this picture of Arctic haze that we have is not quite as we thought it was, and there are differences as you go up in altitude. Now, aerosols, I've mentioned already, they're rather complex, and they're often seen as mixtures of different sources. And this just shows some images taken from data collected, again, a bit north of Norway, in air masses that had been transported across the Arctic from East Asia. So they show quite a mixture here, and with soot residues and a mixture with mineral dust as well. And what's also been shown is that these aerosols can have an impact on cloud properties. And I'm just showing one example here of some data from Barrow in Alaska, where they were looking at the impacts of, if you have more aerosols, this can have an impact on the number of effective cloud condensation nuclei, and in fact produce a larger number of smaller droplets and a higher concentration of droplets. So this was rather nice data showing some of these aerosol cloud interactions. Well, up to now I've spoken mainly about the springtime and the kind of what might be contributing to pollution during the spring. And it's true that for aerosols, the concentrations tend to be lower in the summer because you have more effective washout of aerosol during the summer months. But what about ozone? So ozone shows a different seasonal cycle depending on where you look in the Arctic. But over Greenland, for example, you see a spring and summer maximum in ozone if you look at the seasonal cycle. So here I just wanted to show a kind of case of pollution transport from North America to Greenland. These are some data or some results that we performed looking at some of this polar cap data. So we were making flights over Greenland with the French aircraft. So this shows you carbon monoxide plumes, which are uplifted from fire emissions here over Canada, and also anthropogenic emissions off the northeast coast of the US. And you can see transport of rather fine filaments, so pollution plumes, towards Greenland, and then they were then subsequently transported further into the Arctic. And in fact, what we found in this study, there was quite substantial ozone production during this long-range transport of this pollution from North America to the Arctic. And in fact, so it's this kind of process that may be contributing to the summer ozone maximum that we observe over Greenland. Now, that was pollution transport mainly in the kind of free troposphere, so between about 3 and 8 or 9 kilometers. But in fact, pollution can also be transported into the tropopause region, into the upper troposphere, and indeed into the lower stratosphere. So this shows some rather nice data that was collected during the Strapoletti campaign. So it shows a vertical profile of carbon monoxide collected on balloons. And you can see here 2 enhancements in the carbon monoxide concentrations at around 12 kilometers and around 13 kilometers. And in fact, they combined this data analysis with an analysis of satellite data. So this is carbon monoxide data from the IARSI instrument. And they showed that this pollution here, which was measured over northern Scandinavia, actually had an origin had an Asian origin here, coming from anthropogenic emissions and also from fires. And also there was an impact of Alaskan fires that were also transported into this air mass before it was sampled here over northern Scandinavia. Now this is interesting because, for example, if ozone was being produced in this air mass, it could have a larger radiative impact, because ozone has a more of an impact on the radiation budget if it's transported into the middle and upper troposphere. But what about models? It's important because to kind of see how models are doing, because they obviously are tools for predicting the future, or the future evolution of atmospheric composition, for example, and their impacts. So this shows some comparisons between observed seasonal cycles and different models that have been run for the current IPCC exercise. So again, you've got seasonal cycles, this time of carbon monoxide, which is, as I mentioned, a precursor to ozone, and also black carbon. But in fact, what we see is that the models have problems simulating the seasonal cycle of these pollutants. And we think that for the carbon monoxide, it may be related to emissions, but it does seem to be more related to the lifetime of the carbon monoxide in the atmosphere. Whereas black carbon, the results, you can see there's large variability. Although there have been some recent improvements, particularly models have tried to improve their treatments of loss of the black carbon aerosol by washout. And this just shows one example here from Browse et al., where they improved the treatment of the precipitation loss of black carbon, and they got a better agreement. The data follows this same seasonal cycle, but they got a better agreement in their model. But I'm going to come back to this later in my talk and show you that perhaps this is not the whole story. We can also learn a lot from ice cores about past changes in pollutant levels. So this shows data collected over Greenland. This is black carbon and sulfate as a function of time from 1800 to 2000. And what you see, in fact, is that in the black carbon records, you see significant increases in black carbon between 1900 and 1960. And then you get a kind of drop-off, and then it seems that it may be increasing again. Whereas the sulfate aerosol increased, you do see the similar increase to the black carbon, but then it continued to increase into the mid-1990s. But then there was a rapid decline afterwards in the 2000s. Now this data is data, as I said, from Greenland, and it's mainly influenced by emissions from North America. And these kind of records can also be used to validate model simulations. So again, I'm showing some comparisons between these recent IPCC model simulations. This time the models are being compared with deposition fluxes of black carbon, and also on the bottom here, derived black carbon concentrations in snow. But in general, the models do a better job of reproducing the deposition fluxes than the actual snow concentrations. But it seems, in general, it seems that the model trends are not particularly good, certainly from 1950 onwards. And this seems to be related to the trends in the emissions, although, of course, it could also be related to these issues I mentioned about the aging of the loss processes, how they're treated in the models. So if we think about how the trends of anthropogenic emissions have changed, what I've plotted here is these are the CO emissions, carbon monoxide emissions, for different time periods, so for 1900, 1960, and 2010. And between the first 60 years of the last century, you can see there was this increase in emissions over North America and over Europe, which was certainly contributing to pollution in the Arctic. But then more recently, of course, we've had a kind of decline in these emissions, but then a substantial increase in emissions from Asia. But of course, is this the whole story for the Arctic? Is long-range transport the whole story? So then I want to move on to think about local sources of pollution in the Arctic. So here we need to consider emissions from shipping, from resource extraction related to oil and gas, looking for minerals, extraction of minerals. And of course, associated with this, it's likely there would be increased infrastructure, so development of ports, urbanization. And when you think about local sources of emissions, you also need to think about the Arctic environment, and in particular natural emissions, and the fact that in the Arctic there's rather specific chemical processes and meteorological processes that are going on. So it's current thoughts are that the local pollution is very low or even not important, but that, of course, it's likely to increase in the future. Because we know that there are significant resources in the Arctic. We know that there are significant reserves of oil and gas emissions. We know that there are mineral deposits that people are interested in exploiting. There's the opening of the shipping routes, the Northeast Passage or the Northwest Passage, perhaps increases in tourism, for example, and then there are important regions where there are fisheries. But many of these activities, in fact, are a source of pollution, in particular shipping and extraction of oil and gas and minerals. So first of all, looking at shipping, this is results from kind of one of the first studies that looked at the impacts of shipping, this time looking at the future impacts on ozone. So what they did is to take an estimate of the shipping emissions, for example, of nitrogen oxide emissions, which are a precursor to ozone, and they looked at the impact of these opening of these shipping routes on ozone concentrations. And in fact, these model calculations showed quite significant increases in surface ozone over the Arctic region. And what they did to look at this in a bit more detail was to compare, first of all, their model calculations with data collected in Barrow, Alaska. So this shows ozone concentrations as a function of month. Here, this is the observations, are the dots, and then the present day model calculations are the solid line. And then the calculation where you increase the shipping to 2050 shows quite, as I said, substantial increases in the ozone concentrations. And what's interesting about these results is that the ozone levels start to exceed some of the air quality thresholds. So, for example, this is the World Health Organization air quality threshold of 50 parts per billion. And so you're starting to get over this limit with this increase in shipping. But have we actually seen any impact of the ships in the Arctic? Well, yes, this is one of the first studies here. This is a very recent study looking at the impact of cruise ships on black carbon. So they took data from Ny-Ålesund and from Spitsbergen and compared data that was collected over a number of years. They compared summertime black carbon concentrations with when there were ships in the harbour and when there weren't. And they found differences that were significant between the black carbon concentrations with and without ships in the harbour. And people have also there've been studies looking at the climate impacts of shipping. I'm not going to go into this slide in a lot of detail, but one result was particularly interesting from this study is that there's a lot of discussion about proposed regulation of ship emissions. And in particular, it's likely that the sulfur dioxide emissions from ships will be regulated. But in fact, sulfur dioxide produces sulfate, which cools the atmosphere. So if you reduce sulfate, then you're going to warm the atmosphere. You have the opposite effect. So this is a kind of, you're kind of winning because you might improve air quality because you have less sulfate aerosol, but then on the other hand, you have a negative climate penalty. And this study also showed that there was an important contribution to radiative forcing from ozone and also from black carbon. But another fairly recent study or report that was put together by an Arctic Council expert group on black carbon, where they looked at the impacts of black carbon emissions in Arctic Council countries, so in the US, Canada, Russia, and Nordic countries, compared to the rest of the world. So this is the ROW here. And what they found was that the near Arctic black carbon emissions have a much higher impact on local Arctic climate. And the same was true for increasing ship emissions in the Arctic. Because you're emitting the black carbon locally, you can have a much higher impact. But of course, there are many uncertainties related to ship emissions. There's very little data that's actually been collected in the Arctic about how ships behave, how much they emit under Arctic conditions. And I'm just showing one example here from a review by Lack et al. And what it shows is, in fact, that ships emit more soot or black carbon at low engine loads or speeds. And this is because ships are not really tuned to run at low speeds. So one could imagine that perhaps in the Arctic, ships are likely to travel more slowly. So are they going to emit more black carbon in the Arctic? We've already seen this figure as well. So this is a paper a very recent study looking at future emission scenarios for shipping. And in particular, looking at a new class of ship that could go directly across the pole. So that, in fact, shipping companies are now looking at building kind of light icebreakers which could sail directly across the pole. Another important, perhaps interesting aspect to think about is that we may have increased maritime access in the Arctic Ocean, but we could probably have less access over the land due to the melting permafrost. So will there be a change in the transport patterns? So finally, just to finish, I wanted to talk about resource extraction. Of course, between the 1960s and 2004, well, in the 1960s was rather little resource extraction, but by the 2000s, there in fact is quite a lot of resource extraction going on, particularly in Russia. And I just wanted to show one result here, which is a very new study that's just been submitted, where they've produced a new emission data set, particularly looking at oil and gas flaring emissions in Russia. And they found that this is a very significant local source of black carbon in the Arctic. It may account for 40 to 50% of surface Arctic black carbon. And in fact, this study showed that in their model calculations, this greatly improved the comparison with data. So this really comes to question a bit I think it's in addition to the studies where people were trying to tune their wet deposition schemes, for example, that there are these new local emissions in the Arctic which need to be taken into account. So if we want to consider future Arctic emissions, we really need to think about not only Asia and increasing emissions over Asia, but we also need to think about what's actually going on in the Arctic and to be able to better predict emissions from shipping, from resource extraction, and associated emissions from industrialization and urbanization. And then just to finish, I just want to mention again the fact that if we're putting local emissions into the Arctic, then there are very specific processes that we need to consider. For example, there are snow emissions that we need to think about. Halogens, for example, can be emitted from snow, and there are also many sources of natural aerosols. So just to conclude then, the points I'd like to make are that long-range transport, of course, has been important in the past, although the trends that we've seen in ice cores are not particularly clear for the moment, the reasons for the trends. But of course, it will continue to be important in the future. Local sources of pollution are not very well quantified, and they're probably already important. And they're likely to increase in the future, although the scenarios are very uncertain. And then we need to think about this in the context of the natural environment in the Arctic, and also within the context of climate change. So, thank you.